Okay, good afternoon, everyone. Thank you for being here today. My name is Mohammed Al-Sakhawi, and I'm here today with my colleagues Jeff Albert and Mike Cave. And today we'll be talking to you about Openstack and the Canadian ARC. So before I do that, I'll just go first with the agenda that we have for today. So first, we'll be explaining what is ARC, what's Advanced Research Computing, for those not familiar with the term itself. And then we'll be looking at ARC in Canada. What kind of organizations support ARC in Canada? What is the history of OpenStack? So when we started looking at OpenStack and using it in our national platform, our national cloud platform that exists right now, its sizing, where it's deployed, and so on. And then Jeff will be talking to you about the benefits of the cloud in ARC, specifically in a very unique use case, and some success stories. So we have lots of users right now using the cloud on a day-to-day basis. So there's very interesting stories for our use cases, basically, in the cloud. And finally, we'll be talking to you about the storage in the cloud. So we put lots of effort into thinking about the storage solution that we have for our cloud because it grows a lot. So Mike will be talking more about how basically we went through the whole process of it and what we use right now. So first, advanced research computing. I see very familiar faces here from scientific interest group, so I think many of you might know what's advanced research computing. But just to reiterate quickly on that, it's basically computing infrastructure and the services for research needs. So on a day-to-day basis, researchers use computing to do simulations, molecular dynamics, and whatever fields. And traditionally, those were large computations, so lots of number crunching and large data sets. This, however, and basically this translates in a system that are very huge. So basically large number of cores, large storage, high IOPS storage, low latency interconnect, which normally were labeled HPC clusters or supercomputers. However, this realm has been changing in the past 7 to 8 years, very similar to the change in the industry itself as well. So now software stacks are becoming more and more complex. You don't have now the single binary that you take to your system and execute it there. It's actually now stacking for the software. So you have different pieces of software have to work together to be delivered from the user's perspective at least. You need isolated and private environments to operate most of software stacks right now. So the idea of sharing that we had in Apache vHost and similar software is not becoming more popular anymore. It's actually becoming less popular. And the accelerator-based computing, this is now becoming also a hype or something that's being used very much right now. So GPUs, FPGAs, and TPUs are being requested in research work and also in the industry as well. So ARC in Canada started very similar to that. So we basically started with supercomputers, but we have, with time, evolved from that to actually include additional services as well to our platform. So right now we run supercomputers, we run infrastructure as a service through our cloud platforms, backend as a service, big data platforms, VDI, and other services as well. So we're continuously adding to our software stack more and more service to support researchers. We're in favor always of structured things rather than one-offs. So we always look for technology that are here to stay and basically develop a process around them and deliver them to our customers. Organizations support ARC in Canada. There is regional organizations and there is national organizations. So starting from the right-hand side, we have ACENET, which covers the eastern part of Canada. So New Brunswick, Nova Scotia, Prince Edward Island, Newfoundland. And then we have Compute Ontario, which covers Ontario, Calcul, Quebec, which covers Quebec, and Westgrid, which covers the western provinces, Alberta, Saskatchewan, Manitoba, and BC. The national coordinating body between them is the Compute Canada, which lives in Toronto. And basically, this is the bigger picture that we have the regional entities, and we have also the national coordinating entity. We all work as big part of national teams. So although staff might be employed by certain regions, they're actually all part of national teams at the end of the day. So just to give you an idea of what systems we have, so we operate 4 major supercomputers. They're ranked 59, 190, and 271 on the top 500 list. The 4th one was just commissioned less than a month ago, so that we don't have a number for that yet. Between those systems, we have 190,000 physical CPU cores. We have 5 major cloud deployments, around 15,000 physical cores between them, around 7 petabytes of Ceph, and that's why I mentioned earlier that we gave our Ceph storage very much thought, basically. Since our commissioning of the VM as of the national platform in 2014, we have had 1.4 million VMs created. So basically, on an average year, we have 280,000 VMs created by the users. And some of these are actually scheduled through schedulers, not actually by hand. We We have 60 petabytes of live storage, which is basically what the users use for SSDs, hard drives as well, to store their data. And we have 60 petabytes of nearline and tape backups. The difference between nearline and tape is basically backups are regular backups. You take a copy and put it somewhere. But nearline is actually integrated with the file systems very closely. So if someone touches a file that's in nearline, it will actually be retrieved from tape and brought back to the file system. And when the file is not used anymore, it gets pushed back to nearline. So sort of offloading where to store the data. So adoption of OpenStack. So we started first, as I mentioned, by realizing the need. So we understood that the realm is changing. The HPC clusters will not deliver in the entirety of the research needs anymore. So we started by looking at, in 2014, deploying 2 main clouds. And they were located in the east and the western part of the country. And they were actually, for convenience, they were named West Cloud and East Cloud. We started with the Icehouse release, and we only deployed the services that we need. So as most of you are aware, earlier days of OpenStack, there was lots of services that appeared and then disappeared. So we didn't want to be on the wagon of services that basically disappear and we're left to support them. So we went also through phases of upgrades and migrations. And right now we have, as I mentioned, 5 major clouds. They're located in Ontario, in BC, and in Quebec as well. So the national cloud platform, it consists of those 5 major clouds. They're entirely x86 clouds. However, we offer our users as well GPUs and FPGAs flavors. So basically, a user can spin up a VM that has GPUs attached or FPGAs attached as well. We use safe backends for most of our storage, or actually for entirety of our storage. We use 25 gig Ethernet interconnect, or 10 gig. And there is also backbone links to connect the cloud sites. So the cloud sites are located in western part of the country, as I mentioned, as well as Quebec and Ontario. And we have backbone links to allow high performance communication between them. Right now, the links are varying speeds, but we're looking to have them at 100 gig at some point in the future. So the national cloud team, which basically I'm part of, and the guys here also are part of, it's responsible for the architecture, the deployment, and the operation of the national cloud platform. On a day-to-day basis, we basically look at the national platform, and if there's any issues, we resolve it, or whenever there is a new commissioning for new cloud, we actually look at that and basically make architectural decisions for that. We provide also user support, so we have analysts in our team that actually help out users on a day-to-day basis. If there is any issue inside the VM, we can provide support on that as well. The team is entirely distributed, so we have memberships from the entirety, as I mentioned, of the country, and basically it has members from 4 different time zones in the country. And just before I hand this over to Jeff to talk to you about the benefits of the cloud platform, we just have a chance to have a look at the team. And some of us are actually in attendance here today, so feel free to contact us right after this session if you have any questions. So Jeff.
Thank you.
Here you go.
Hi, everyone. My name is Jeff Albert. I'm a member of the Compute Canada Cloud National Team with Mohammed and Mike and everyone else in this photo. And I want to spend a little bit of time talking about why we ended up moving towards the cloud environment for advanced research computing and the unique benefits of the cloud environment. So as Mohammed alluded to, obviously the history of ARC, particularly in Canada, has been large supercomputers and remains still a significant portion of that system. But things are changing and workloads are definitely changing. And so there are some unique benefits that cloud offers. One of the really big ones is agility right out of the gate. So if you're scheduling jobs on a large HPC cluster, the cycles there are very valuable. Getting them scheduled can be very tricky. And once you do get those cycles scheduled, you really want to make sure that you get the most out of them. So a real challenge for people is developing workloads that they know are going to perform well and that are going to schedule well. There's not necessarily an easy way to do that, scheduling on the big production clusters. So prototyping is something that a lot of researchers want to use the cloud for, in the sense that they're able to produce a tiny little ship-in-a-bottle HPC environment and try out their workloads there with some control over how that's going to execute and the opportunity to iterate fairly painlessly. Experimental systems are another option there. Because you can build out your infrastructure as you want it inside a cloud tenant, researchers can try out the design of an HPC or possibly a hybrid system that they're not sure will work and iterate on that over time. And of course, there's the collaborative infrastructure component of it. So Canada is a large and geographically distant region. You often work with people both across that large country and around the world. Being able to collaborate with something that's available to everyone through the internet and doesn't necessarily require physical presence is a major benefit of cloud. Another thing that we can offer through the cloud is scalability. HPC burst capacity is a big thing that we're able to offer now using the cloud environment. So we can schedule VMs that can opportunistically make themselves available to extend the capacity of HPC clusters. Internet scale applications, which is the second buzzwordiest thing that I will say in this slide deck, which sounds kind of trite, but imagine that you're working on a research project that suddenly gains either international attention or media attention. Suddenly your portal to that data or your website for that project is going to find itself under some pretty significant load. If you're just running that off one server in somebody's data center somewhere, it's unlikely that you're going to be able to scale to that level of attention. The cloud and the flexibility of the cloud give you a fairly robust way to scale up to that internet scale level of attention. And finally, multi-cloud availability. So we're fortunate enough to be running clouds in 5 sites across the country. Those sites are, as I'll get to in a bit, fairly uniformly configured. So if you are a savvy tenant user of those clouds, you can set up multi-cloud availability, particularly for stateless or web type applications, relatively painlessly and have complete geo-replicated availability across the country. Flexibility. So client-driven infrastructure design. Again, if you've worked in the research departments at universities, commonly you are accustomed to working directly with an IT group to get your IT infrastructure deployed, and often that's through a project process where you'll request a project and you'll have it provisioned for you. There will be an end to that project, and then if you need more, you're cycling again. The cloud obviously provides a method for projects to move directly to provisioning their own infrastructure, to have people who are technically competent moving between those projects and helping them design those projects for them in a much more ad hoc and live scale kind of way. A surprising thing that we didn't really expect so much when we started doing this, but people have really caught into, is complete software environment control. So when you're running jobs in an HPC context, it's sort of an attempt to meet everyone in the middle in terms of software dependencies, library availability, kernel module availability, kernel versions. If you have jobs that require very particular things, or if you have jobs that require libraries or kernel modules that would not work well for other people's workloads, it's often fairly difficult to get an HPC environment that does exactly what you want. And there are some tools to help work around that. But the cloud gives you an opportunity to develop an environment that is absolutely perfectly tailor-made to your set of requirements and have that total end-to-end control from the kernel up of your software execution environment. And finally, lifecycle and availability control. So of course, you're beholden to no one in the cloud. You can set your own schedule for updates and restarts, and you can set things to be changed at a time that's convenient or appropriate to your workload. Persistence is something that has sort of been danced around the edge of in advanced research computing for quite a while. So obviously, HPC is all about executing a job, possibly a billion times, possibly once, but at great expense. But once it's done, it's typically done. And generally, there's not the idea of persistence that lasts past the end of that job. So when you want to do websites or portals or long-running databases, which are frequently now being pursued as part of application workloads in advanced research computing, you need something that's going to host those workloads for you. And again, 1 or 2 servers in a data center typically will not scale to that need. Cloud gives you the opportunity to run long-lived production-grade applications in the manner that suits your workload best. We're backing it with a massively replicated Ceph data store. So again, you're getting that benefit of enterprise-grade storage reliability and availability kind of for free. Our cloud national team is providing that infrastructure, and it's not something that the cloud tenants necessarily need to worry about too much. And finally, the buzzwordiest item in this slide deck, API-enabled dynamic lifecycle management, which really just means that you have the freedom, both with tooling that you can tie directly into with things like your CI/CD pipelines or whatever, to set up a lifecycle management structure that's defined in code, that's manageable, that's iterable by all the members of your team. And so in order to make this work, and knowing that we were going to have a large distributed team across the country, different time zones, different languages, we decided to go with a national distributed team approach to building production clouds. Across the board, we knew that deployment was going to be a crucial tool, so we standardized on IPMI BMC control for remote console, remote power, remote rebuild capability, and we have been standardizing together on installation and orchestration of OpenStack using OpenStack Ansible, which stages, deploys, and configures OpenStack for us. Now, of course, OpenStack Ansible is sort of a choose-your-own-adventure kind of situation. Your inventory is much up to you, but beyond that, once you've run OpenStack Ansible, you have an OpenStack. There's quite a bit of site-specific additional play and glue code that we need to add on top of that. So we layer that in as a post task in our OpenStack Ansible environment. We made a decision early on in the process to standardize on everyone operating directly out of a revision control repository, which we decided would be the single source of truth. So we have separate feature branches for every issue that we're working on in progress. We have protected deployment branches for dev, prod, and remote sites. And we run continuous integration testing automatically on every commit, basic syntax checking, Python syntax checking, what have you. And the goal was that we should be able to deploy the entire thing at any time with just the data in Git. So in the event of a complete catastrophic failure, notwithstanding the state data that's going to be in the database, everything else should be completely reproducible just by checking out what we've got in our Git repository, rerunning OpenStack Ansible, and moving on with our lives. The goal there was really to remove that sort of iceberg of unknown configuration. Often in complex environments, you'll end up in a situation where you started from a known good point, whether that was an image or something in a repo, and then this didn't work or that didn't work, so you make a few changes here and there. Now you've deviated an unknown amount from your starting point, and if that stuff's not in revision control, you're never going to find it again. We also made a fairly significant investment early on in observability. So we're doing metric collection with Prometheus. Lightweight pull-only exporters written in Go, which means they're fairly lightweight. So I had some concerns about running an agent directly on our OpenStack control plane infrastructure where there's the potential for some bottlenecking, but Prometheus has proved lightweight enough to not get in the way, and the metrics that it provides are just phenomenal. It's got its own hyper-efficient time series data store server, and then we're backing that with durable storage into InfluxDB. Prometheus actually does not really want you to hold long-term data in its own time series store, so we're storing that with the InfluxDB behind the scenes. And of course, everyone's favorite visualization tool, Grafana. So if you're using Prometheus, and particularly some of the more common exporters like Node Exporter, there are some really great community dashboards for Grafana. But if you take a look at the queries that those are running, it's fairly easy to move pretty quickly into developing custom dashboards of your own. So we've got a couple of custom dashboards I'm showing here, which describe our OpenStack environment. Let's see if I can actually point to it. There we go. So that's cores per hypervisor, hypervisors overall, and then cores per project. So that gives us a really good view, more or less at any time, of how the cloud's being made use of. And then on the bottom, we've got our site-specific information. So particularly the top right graph in that dashboard is a log scale of sort of known indicators of trouble. If that log scale starts to show things in the 100 range, I'm very unhappy. If it's things in the 1,000 range, you can't call me. So what are researchers using Compute Canada Clouds for? One of the really big consumers of cycles, and really a consumer of more or less any cycles that we can make available at any given time, are the Bell 2 and Atlas projects, which are high-energy physics projects. Atlas in particular running out of the Large Hadron Collider in Switzerland. We are running currently the most available Tier 2 Atlas site in Canada using virtual HPC nodes, which are VMs scheduled in the cloud. And we're also doing burst and opportunistic servicing of Tier 3 jobs via a project that's running out of UVic's high energy physics department called Cloud Scheduler, which is a project that's aware of cloud resources in many clouds all over the world and will try and just scavenge more or less any cycles that are available, quickly spinning up and spinning down VMs to take advantage of whatever's there. What's neat about that is that it decouples the HPC workload from particular hardware. So we're no longer in an HPC situation where it's like that node or that set of nodes is dedicated to this job for this amount of time. It really is slice and dice, and as cycles become available, spin up a VM, do some work, spin it down. Ideally, as long as you can fit a job inside of an execution window of one of those VMs, that's a win. This is one that was really interesting for me to watch as it was happening in real time. The New Horizons project, which is a probe that NASA launched, which was intended to go out to Pluto and do some high-resolution imaging of it, and potentially to intercept a secondary target past Pluto. So a fairly significant challenge in operating a probe like that. Of course, you're about 7 hours away from it by direct data transfer at any given time, so you can't fly it by wire. You have to plan your navigational solution ahead of time, and you're flying through an asteroid belt. So they started off with some really high-resolution telescopic imagery of the route in question, planned some big data analysis to identify the likely objects that they might encounter during that navigational process, and then, using the cloud, they produced a portal to that data and had teams all over the world compete to try and produce a navigational solution that was most likely to succeed. They were able to successfully navigate to Pluto using that collaboratively sourced navigational solution, and in fact, we're able to go past Pluto and identify a secondary target, Ultima Thule, which they actually successfully intercepted in early January. And finally, GenAP, or GenApp, which is a huge genomics portal and HPC hybrid model. So they've got a giant cloud portal to coordinate HPC processing of genomics data sets, multi-tenant data processing for global access and collaboration. So much less the case of sort of syndicating big data sets around and having people work on them individually at local sites. The idea here is that data is going to be stored in large data sets centrally behind a portal and collaboratively accessible to researchers all over the place. What's neat about that is that there's then that collaboration of direct result sharing. So everything is within that same platform. It's directly comparable in that platform. And they're operating this horizontally scalable platform that's well suited to cloud infrastructure. They've already deployed successfully in several other clouds, and they're coming online in the Compute Canada cloud infrastructure this year. I want to hand it over to Mike to talk a little bit about our storage infrastructure.
Good afternoon, everyone. So as Mohammed and Jeff both alluded to, we've decided after much consideration to go with Ceph as our major backend. So why do we choose Ceph? Mostly because it's scalable, it's open source, and price for performance can't be beat. So the first point is scalability. We're able to scale out the storage in the cluster on an as and when basis. Basically, as we grow, we can add more building blocks without any impact to our clients. It's very, very fluid. We don't need to worry about taking downtimes or outages. We can use a standard building block, which allows for fast expansion, standardized deployment using Ceph Ansible. This gives us real flexibility around time of purchasing and what's available, because one of the great things about Ceph that everybody knows is that you can use consumer-grade hardware if you choose to, and that allows you to buy best of breed, hitting the right price points at the time. So the open source community was a real draw as well, because it's so responsive and so full of experts that whenever you have a question, there's almost always somebody there to help you out. I've had questions basically in the middle of the night where I'm having some kind of an issue, can't figure it out, I'm at the end of my rope, I end up posting a question to the mailing list, and within an hour or 2 hours, I've got somebody asking me more questions, asking for information, even taking the conversation offline if they feel like it's not mail list. So it's just incredibly useful that way. We have a lot of experts in our staff, but to be able to reach out to a larger community like that is incredibly beneficial. Timely releases. We're always getting updates. The community is very aware of any bugs that are coming out. There's great notices if there's a major bug. There was one last summer where if you're running erasure-coded pools, you might have heard, you might have lost all of your data when you updated. So that was communicated within hours of the bug being fixed or found. Bug was taken off, or the release was taken offline, and we went on with our lives. So there's also no vendor lock-in. We don't have to worry about in 5 years the product just going end of life and now you've got to buy the next big thing and migrate all of your data, or go to RFP in our case and have to go to vendors and say what's your best solution and then figure out a migration path for that solution. Price for performance. So there's no upfront cost for the software, obviously. That's a big win. And hardware integrates with our existing infrastructures around our campuses. So we are university-based in a lot of cases. And so it allows us to use hardware we're already familiar with, without having to bring on new APIs and things like that. So we can integrate it really easily. And when you're looking at the performance increases that you get as your cluster expands, you're able to, every time you add a new node, you're getting more network, you're getting more spindles, and you're getting more CPUs. So your expansion doesn't slow you down if you've only got one monolithic piece of hardware with 4 10 gig Ethernet ports in the back. This way you're getting more connections every time. So finally, what are we using our current Ceph for, and where are we going? Well, currently, we're running RBD volumes for our VMs on erasure-coded pools and triple replicated pools. So we've separated the two pools out to allow for kind of you're slower, you've just got a web server running, you don't need high performance, we'll put you into an erasure-coded pool. If you've got a database or you're needing to have really fast operating system access, we'll put you into the triple replicated pool. And that's actually determined on a per project basis. People get to decide what their workload is going to do. We don't try and push anybody one way or the other. We have made the erasure-coded pool the default, so unless you're doing any amount of investigation, you'll probably end up in that pool. So coming online in the near future, hopefully before the end of the year, we're going to be rolling out CephFS using Manila, making it available across all of our projects. I just learned actually here that with the release of Stein, we can have per project file shares rather than global cloud file shares. So we're going to be investigating that pretty heavily going forward. And we want to include in our offering the Ceph object store through the Swift gateway. And we will probably make that available to users that aren't even in the cloud necessarily, because we can access Keystone, which is attached to our federated LDAP service. So we can allow users who may be not cloud users come in, use an object store the way that we want to. We're also going to be doing a geo-replicated object store. So our pilot will be between two of our sites at first that we're connected over a 100 gig link. So we'll be able to move the data and replicate it, hopefully fast enough with lower latency that we won't have to worry too much, and then also allow for multi-gateways, so one at each site accessing the data real time. So that's everything that we had. Yeah, if you want to come up to the microphone. Yeah, go ahead.
Yeah, awesome. How do you do user management? Are those clouds totally separate, or do you have a common Keystone database? And do you bill your users? And how do you do it?
So I can talk a little bit about the technical part of that. So we're running completely standalone cloud infrastructure at each site. Everybody has their own Keystone, but there's identity federated from an upstream service, which is exposed through LDAP to Keystone. So there's not direct project sharing, and then there's not role sharing between the sites. But there is certainly UID sharing between the sites. As far as billing goes, we do yearly utilization. Things are based on project level allocation, but it's not the case that we're directly tying that to dollars.
So
sorry, go ahead.
So every year, our researchers will file out or fill out what we call the RAC, it's a resource allocation. And so they will file this giant amount of paperwork, but it tells us what they need, what they're going to use, and how they're going to grow. It's usually a 4 or 5 year plan, if that's how long your thing is. Sometimes it's just a year. They just need some resources for a little while to do proof of concept things. So if you don't fall into a rack situation where you're asking for a lot of cores or a lot of storage, we'll actually allow you to sign up as on ad hoc basis and get just get resource allocated for a very basic amount of utilization to allow you to test your concept, see if the cloud's the right aspect for you, and kind of move on from there. So that's usually shorter lived. Some of those things are only a month, some of them are up to 6 months, but we try to keep a lid on that.
Maybe to reiterate on that a little bit, so from a resource perspective, if the resources are very huge, you basically have to compete for them. So there's a competition that has to be filed for on an annual basis, and basically if you can get a certain quota from that competition. And as the guys mentioned, basically if it's small, then it's a different process for that. But from a billing perspective, we don't bill the researchers basically money for that.
Where the money usually comes out of is research grants. So when you apply for a research grant to the federal government, parts of that money will be taken off and then put into the Compute Canada funds over time. Also, and at the top level for the Keystone piece, so when you're given an allocation, that allocation is put into your LDAP record. We read that information straight out of your LDAP record and create your project your quotas based on that LDAP information.
Sorry, anyone else?
Hi guys, great talk. I'm curious how you guys keep everything updated across all your 5 different sites. Do you have a strategy for keeping things up to date?
Yeah, it's super easy. So
that's the answer.
So as Mohammed pointed out, we've gone through quite a series of updates and migrations over the last several years. The current iteration of that has been this process that I described of moving into revision control and a sort of an issue and branch driven rollout. That's not something where we're running that at a master level and forcing other sites to all accommodate it. Right now we're all moving towards that central goal. So we've got several sites that are coming from a common trunk and other sites that are sourcing from that trunk and adding stuff onto it. Over time, I suspect that's going to move to a fairly similar central stream, and we'll all be operating together in that central trunk.
So what we're basically working on right now is have common processes across the 5 sites, such that we can go, the next step with upgrades or migrations or whatever, the same pace. So we came from different sites, basically, but we're unifying on the way we deploy things, such that it's easier for us later on to upgrade and maintain the infrastructure.
And one of the benefits of the national team infrastructure is that we're able to share triage duties and configuration management duties across the sites. So we've got people in different time zones and across the country who are able to directly administer each of the cloud sites. We share credentials, we have administrative access, and we can move directly between those sites. We're really collaborating at a national level.
Thank you.
Thanks for your time. I'm curious, if someone were to compromise your security, what would be like your worst case? What would really worry you about someone misusing your infrastructure?
So are you talking from like tenant's perspective, or are you?
From a tenant as well as like the whole thing.
Well, the whole thing we probably won't be discussing it here anyway. But yeah, from a VM perspective, we're working right now in like more and more, collaborating with our users, basically educate them also in security practice and so on. But there's lots of things, we're a public cloud provider, so whatever applies to public cloud providers applies to us as well.
Is there a degree of isolation between cloud services and your HPC?
So the question was, is there a separation between the HPC services and the cloud services? Yes. So 4 of our cloud sites are on site with an HPC cluster. They aren't tightly integrated yet,
Not yet.
but we are moving in that direction. So one of our sites that Jeff and I are working on right now, we're actually attaching a cloud kind of to the front end of their HPC cluster so that they can bring their nearline data in and start showing that through their portals.
Would it be directly, or would it be some kind of a proxy between that prevents the things being pushed back to maintain the isolation?
So I'll hesitate to say that there's a solid answer to that question yet, since it's all in progress. I can see the point you're getting at, of course, and I agree entirely. Yes, there will likely be some layer of indirection there that's intended to provide one-way access.
Yep.
Does your team provide advanced user support for the researchers? You have a support role, or do you have a own support team for helping them actually consuming the resources?
So I think the team itself has mostly admins at the administration side, plus also we have analysts that can actually help you inside your project. But the bigger Compute Canada / the regional entities realm, there is 200 people basically in it from different specializations of science basically. So if you have a specific molecular dynamics project, there's probably someone within the entirety of Compute Canada and the regional entities that actually have the expertise for that. But basically, the cloud national team is responsible for the operations, but we also include some, help, user support with how to use the cloud and the VMs and so on. But if you need something very scientific, we actually have analysts that are very specific to science categories, basically, for that. Does that answer your question?
Just to kind of expand on it a little bit, yeah, we've got, so on our team we have, say, Chris Giroux, who is an absolutely fantastic analyst. He's also an analyst for his own institution. So if we have some issues, he'll help triage it, and then if it's somebody on his campus, he'll actually go to their office and just work with them and work through the whole process. And we have people on our campuses like that, and you've got people on your campus. Sure. So we will triage the ticket, realize who needs the help, and then get that person the right help from their own institution with somebody they're probably familiar with.
Ivan Adams from IHS Market. So I have one specific question. You mentioned earlier about some of the hardware that you're using, GPUs, FPGAs. Can you highlight any specific use cases whereby you're using one versus the other? What decision factor are you factoring into, cases where you're using a GPU versus an FPGA?
Yep. So I can't speak to the actual execution part because basically it's user-driven, but we have some users that have load-specific, whether it's CUDA for GPUs and so on, or FPGA-driven, such as whatever IBs that exist right now. So it's entirely derived by our users. So basically users specify what they need from a user's perspective, but we provision that for them. So thank you very much for your time today, and you'll be around if you have any questions.